You are sitting in a window seat at 35,000 feet, quietly sipping your coffee. Inside the cabin, everything is calm, quiet, and perfectly serene. But just 3 feet away, outside that window, a continuous, violent explosion is underway. A commercial jet engine is a roaring tornado of fire, swallowing the sky, crushing it, and shooting it out at Mach speed to shove a 400,000-pound machine through the air at 600 miles per hour. This diagram illustrates the Carnot efficiency limit. It shows that an engine becomes more powerful and fuel-efficient as combustion chamber temperature increases. To maximize performance, engineers push internal temperatures as high as possible, with efficiency climbing concurrently. Here is the problem. The standard metals used to build these engines melt into a puddle at roughly 1,300 degrees Celsius. Yet, to reach modern efficiency standards, the core of the engine must operate at temperatures reaching 2,000 degrees, nearly 700 degrees past the point where the metal should physically fail. This means that every modern flight relies on a machine forced to operate continuously inside an environment that is designed to melt it. Taming that raging inferno requires a digital brain called the Full Authority Digital Engine Control, or FADEC. This computer has total authority over the engine's operating parameters, regulating the fire so precisely that the engine can perform at maximum efficiency for any given flight condition. This technical drawing shows the internal layout of the FADEC system. The computer calculates inputs 70 times per second while surviving massive thermal loads and 20 G shocks. This rugged physical design is critical, as 20% of aircraft electronic failures are caused by vibration. But the digital control is only the first layer of survival. Once the fuel is ignited, the resulting explosive gas has nowhere to go but out the back. As it expands, it slams directly into the high-pressure turbine blades. The mechanical stress on these blades is staggering. On takeoff, each blade generates as much power as a Formula One car, while spinning creates a centrifugal outward pull equal to the weight of 2 double-decker buses. Under these extreme conditions, standard metals will naturally stretch and snap. Because of that immense centrifugal stretching and the 2,000-degree heat, standard materials like steel or titanium simply cannot survive the environment inside a jet engine core. To fight the heat, engineers turned to nickel superalloys. By adding chromium and cobalt, they created materials that could handle temperatures hundreds of degrees hotter than the steel used in the first jet engines. However, even these alloys have a microscopic flaw. Most metal is made of millions of tiny individual grains. Under extreme heat and rotation, the boundaries between those grains become weak points where the metal starts to crack and pull apart. Solving this requires a specialized manufacturing process that begins with the ancient technique of lost wax investment casting. Engineers create a wax replica of the blade and coat it in a ceramic slurry to create a hollow mold. This shows how engineers manipulate the cooling of the liquid metal inside that mold. By forcing the alloy to solidify as a single continuous crystal, they eliminate grain boundaries entirely. This uniform single crystal lattice allows the blade to resist the crushing centrifugal tension of flight. While single crystal metallurgy prevents the blade from ripping itself apart, it still doesn't explain how the metal survives temperatures that are hundreds of degrees above its melting point. A look inside the turbine blade reveals the solution. To survive the heat, the blades are manufactured as hollow shells rather than solid blocks of metal. This cross-sectional diagram illustrates the internal cooling system. Cold air is forced through an intricate maze of rib-turbulated passages and pin fins, extracting thermal energy. The green arrows represent film cooling, internal air ejected through microscopic holes, creating a protective boundary layer. This ejected air acts like an invisible force field, literally preventing the 2,000-degree gas from ever physically touching the surface of the blade. By shielding its components with this boundary layer of cool air, the engine survives by actively manipulating fluid dynamics to resist its own internal environment. The massive energy generated inside that core is primarily a means to an end. Despite all the engineering we've explored, that fiery exhaust gas only provides about 20% of the airplane's total thrust. This image highlights the true source of movement, the massive front fan. The core's primary job is providing power to spin these blades. They grab massive amounts of cold air and shove it backward, bypassing the fire entirely to generate 80%